Thanks everyone for coming. I am aware that this is your last session before freedom for the day, so I'm hopeful to make this both interesting and relatively brief. My name is David Morrison. I am a tech lead and software engineer on the compute infrastructure team at Yelp. And we exist to connect people with great local businesses. And in particular, my team exists to build, support, and run all of the infrastructure that allows us to accomplish this mission. Now, the title of my talk is Getting the Most Out of Your Mesos, so obviously I'm going to be talking about Mesos. It does play a critical part of our infrastructure, and it has for several years. I'm going to assume a relatively good level of familiarity with Mesos. I'm not going to explain how Mesos works, for example. But if you're not familiar with Mesos, you can think of it as just a API for programming against a distributed cluster. So you can, as an application developer, you can write your application without worrying about details of what machine this is going to get scheduled on, for example. So there's kind of two stories that I'm going to highlight in my talk. The first story is really just talking about the history of Mesos at Yelp. So I'm going to be talking about our service-oriented architecture and how we grew that on top of Apache Mesos. The second story, which I think and I hope will apply regardless of what specific technologies you're using, is really more about data. So I'm going to be talking about how we gained observability into our Mesos clusters. Observability is sort of the hot buzzword that's been going around a lot recently. And I'm going to take a few liberties, and I'd like to invent a new buzzword because buzzwords are fun. And I'm going to talk about how we use this data to move from observability to what I call predictability. And I will define what I mean by that as the talk goes on. So I want to give you a few examples of what Mesos looks like at Yelp. We have, this is a non-exhaustive list, but Pasta is one of the first things that we developed at Yelp that takes advantage of Mesos. Pasta acts as the glue between the developer writing their code on their dev box and getting their code deployed into production. So Pasta encompasses Mesos frameworks like Marathon and Kronos. It manages a Jenkins pipeline so that when you deploy a new version of your service, it gets deployed to the right places and all of the tests and everything get run. This is open source. You can find it on our GitHub. A different example of a Mesos framework that we have is Tron. This is our answer to Kronos. Tron is a distributed batch framework, so it allows our developers to run long-running batch workloads or short-running batch workloads in a distributed fashion. This is also open source. It's on our GitHub. Jolt is an internal tool that we use for doing unit and integration tests. So to give you a bit of an idea of what that looks like, we have on the order of 100,000 unit and integration tests that we run just for our Yelp main application. That is the code that runs yelp.com. And we run those 100,000 tests probably 300 or 400 times a day. And using Mesos, we're able to do one run of these in about 15 minutes. We also, this year, we have started looking at Spark on Mesos to handle our various machine learning and data processing workloads. And that's something that is starting to take off and become very popular at Yelp. So these are a few examples of the types of things that we use Mesos for. And this graph shows how adoption of some of these tools has progressed. So we started using Mesos in early 2014. This was 2 years before Mesos version 1 was released. So we were a pretty early adopter. The blue line that is there shows Pasta services. So these are things that run on top of Marathon. So for example, our Yelp main application, the thing that powers Yelp.com, is a Pasta service that runs on top of Mesos. And we completed the transition from just sort of running on dedicated servers onto Mesos for Yelp main about a year and a half ago. You can see that the number of services that we have on Mesos has grown pretty substantially. At the beginning of this year, we had about 400 different services that were running using Pasta. The green line shows Kronos batch jobs. I mentioned Tron as well, as we are hoping to start transitioning things away from Kronos and onto Tron. But we still have something on the order of 600 different batch jobs that run on top of Kronos. So we operate at, and this isn't even showing things like Spark, our unit testing workloads. We make heavy use of Mesos at Yelp. I'm going to take a slight diversion here because a question that always comes up, especially in the last year or so, is why are we still using Mesos? And people don't always come out and say this, but the elephant that's in the room when I ask this question, represented by this cute little guy, is Kubernetes. And I think there's a number of really good reasons as to why we're still on Mesos. One is sort of organizational velocity. We've been using Mesos for a long time. Our developers are used to it. We have tooling built up around it. We know how it works. We know how it doesn't work. We just are able to do a lot with Mesos right now. The second answer is that a lot of our workloads, actually Mesos is really good for. Mesos was originally designed to handle a lot of the batch workloads that we do a lot of. And the third answer is that we actually are looking into Kubernetes. We have a couple small Kubernetes clusters right now that we have some services running on. And we're kind of evaluating that to see what the landscape looks like. But I'm not really going to talk about Kubernetes for this talk. This is really focused on how we're using Mesos. So I mentioned observability. And for us, observability really means what are our Mesos clusters actually doing? And what are the services that are running on top of our clusters actually doing? And we've got observability. We have charts and dashboards and all kinds of stuff that we can look at to see how things are healthy. This chart is showing the state of one particular service. We track all of the different instances or copies of that service that are running, and we see what their CPU allocation, their memory usage, how many copies are running. And even just by looking at this graph, you could see that, about 8 o'clock in the morning or so, we had a bunch of new copies of this service that started up. Observability also covers things like logging and tracing and aggregation, and we can do this. We use Zipkin for tracing. We have Splunk for log aggregation. And so at any given time, it's pretty easy for us to identify, we have a bunch of hosts in the cluster that are impaired, a particular service is impaired, and we can start going in and trying to troubleshoot and figure out what's wrong. But I want to motivate the second story of my talk, and the reason why I want to invent a new buzzword, by a couple of stories. We had a few problems in 2017. So in 2017, we started really taking off, and our Mesos clusters really started to scale up. And we started to see, one day we saw a graph that looked kind of like this. I've taken all the y-axes off of these graphs because these are proprietary numbers, but the blue line here represents requests per second. The orange line represents errors served. And you can see that for the space of about an hour, we were serving our users a lot of errors. We looked at that, and we went through the whole incident response procedure, and we figured out what was wrong, and we mitigated, and we moved on, and then it happened again. And it happened again, and again, and again, and again, and again. And we had these all happen in the space of about 2 weeks. And what we realized is we could observe what was going on. What happened here is that we started to hit the limits of the number of services that a single instance of Marathon could support. And we also knew what the answer here was. The answer, of course, is to shard Marathon. That is, run multiple copies of Marathon at the same time and distribute your services across them. So this is fine. What we didn't know is, well, how many instances of Marathon do we need? We have some idea of how much one instance can support, but it would have been really nice to have some hard numbers around this. In other words, it would have been really nice to be able to predict what we needed to do. Another example that is the same sort of issue. A little bit later in 2017, we had a problem where we started to spin up a whole bunch of batch jobs all at once on the same cluster. And what we thought was going wrong at the time was that we were running into limits with Mesos in terms of how many frameworks that it could support, because each batch workload was running its own Mesos framework. So what we did is we took all of these frameworks and we moved them to a different cluster because they needed to keep working, but we didn't want them to impair our core website. And then we started running a few experiments, and what we found out is actually the number of frameworks didn't really matter that much. So this graph is showing on the bottom, it's showing the number of frameworks, and on the y-axis is showing the response timings of some of the various Mesos APIs. And what we discovered is that we were able to run somewhere up to 1,000 frameworks or so before our response timings really got bad. And so this was sort of our first foray into what I call predictability. And you might have gotten the hint by now, but predictability is really the ability to understand what your systems are going to do before they get into production. Observability is being able to understand what your systems are doing while they're in production. There's a couple of different ways that you can achieve predictability, and we've been working on both of them. One is that you can create an isolated environment that resembles your production environment, and you can start running tests on it. So one thing that we've built is a system to load test Apache Mesos. We have a number of questions that we'd like to be able to answer in terms of, for example, how many frameworks does it support? And the pattern for this is pretty straightforward. It follows your sort of standard scientific experimental design. What we have is a YAML file where you write down what your experiment's going to look like. You say how many machines you want in your cluster that you're going to load test. You tell it what code to actually run on the cluster. You tell it how to run that code. You tell it what metrics to aggregate, all of those sorts of things. We then have a benchmarking harness that takes as input that YAML file, and it does all the stuff needed to set up the experiment. So it looks at the YAML, it pulls down code from Git, it runs the code, it spins up the cluster, it then collects all of the metrics from the experiment, and then it shuts the cluster down. All of this is automated because you don't want to have a human remembering to do all of these steps. They're going to forget. And of course, this is running on a real live Mesos cluster. And one of the key components, in my view, of what I'm calling predictability is not just being able to do this thing once and then move on, but you really need to archive and be able to perform data analysis on your experiment. This is really hard to do in a distributed system because how are you going to archive 1,000 CPUs and what they all did? We do the next best thing, so we have code that will just go to all of the nodes in the cluster, and it will pull down all of the logs that we might care about. We pull down the Mesos agent logs, we pull down the Mesos master logs, we pull down all of the standard out, standard error from the services. Everything that looks like a log file that we might care about, we pull down. And all of this gets stuffed inside of a Docker image with a Jupyter notebook and some nice CSV files with all of the data that's already been parsed. And then you can open up the Jupyter notebook, you can do all of the data analysis that you want to, and then you save it all and you upload it to your Docker registry. Then 6 months down the line, when you can't remember, why did I make this decision, or what was the rationale behind our particular mitigation in this incident, or anything like that, you can just download the image. You can rerun the code if you want to, and it's in the exact state that it was in at the time you made the decision. This is a really key component for me of what I'm calling predictability, is the ability to, in the future, remember why you did things. And Docker and Jupyter are really great tools for being able to accomplish this. Just going to give you a quick example of what this looks like. We recently were considering whether we wanted to use the Docker Containerizer or the Mesos UCR in our applications. If you're not familiar, the Mesos UCR is the Universal Container Runtime. It's basically the Mesos version of Docker. And so we ran this load testing script to try to understand the performance of Docker versus the UCR. And one of the things that we found is that Docker is pretty slow. This graph here is showing the time that it took for us to launch 10,000 Docker containers across a cluster with, I think, around 1,000 CPUs. And we graphed the distribution of these times. And these containers were really simple. We just pulled down the latest Ubuntu image, and we echoed hello world and exited. And so this graph is showing that, on average, this process took around 60 seconds. In the worst case, it was taking close to 3 minutes. And we were able to then run the same experiment with the Mesos Universal Container Runtime. And the slowest execution for doing the exact same Docker image was 8 seconds. And this is all saved. We have the data. We can share it with you if you want to see it. But this is an example of how we're able to use load testing to make decisions about our large-scale clusters. But there's a second component to predictability, and that is that, well, sometimes you can just run a load test like this, but sometimes you really can't, because you depend on some particular property of your production environment. We have an example of this in that all of our servers are running on Amazon EC2. And like everybody else in the world, we want to auto-scale our clusters because we have predictable demand and predictable traffic patterns, and sometimes we need more instances, sometimes we need less. So we wrote an autoscaler, and we would make some changes to it. We would test them in our test environment. We would run all of our unit tests against it. Everything would pass, and we would say, okay, this looks good, let's deploy it. And then, because of some particular peculiarity in our production environment, the autoscaler would go haywire, and it would scale everything up, and we would pay Amazon lots of extra money. Or, in some ways worse, we would scale everything down, and all of our customers would start getting errors because we didn't have capacity. And the key thing here is that this only happened in production because of particular things about our production traffic. So how do you address that? Well, we wrote a new autoscaler. We have a number of different goals with this autoscaler called Clusterman. But the key thing here is that we want to start with our data. We want to be able to look at production data and use that without necessarily impacting our production traffic. So for our clusters, we store all of the data about the clusters. This includes system metrics. This includes application level metrics. All of this goes into a data store, and we provide a nice API for interacting with that data store, both for getting stuff in and out. And the other observation that we had is, as we're trying to start co-locating more applications on the same cluster, some applications have different requirements than others, and perhaps want to scale up and down in different ways. And so we created a pluggable architecture where the application owner can tell us how many resources they think they're going to need. and they can just write a few lines of Python code, or they can create something very complicated to tell us what they think they need, and all of that data can then be fed into our core auto-scaling logic, which will synthesize those results and actually interact with our cloud provider, in this case AWS. But that's all kind of tangential to what I want to talk about, which is predictability part 2, which is simulation. Because of the way that we designed Clusterman, all of these components are modular and fairly separate from each other, which means that instead of interacting with AWS, we can just create a simulated AWS and a simulated Mesos and have our autoscaler interact with that. Now, this is really cool because we can take all of our production traffic, we can take all of the real signals, we can take all of the real autoscaling logic, and we can run it as a simulation to see what might happen. We can make changes to our signals, we can make changes to the autoscaling logic, and we can run it to see what might happen. We can even do things like, well, what happens if we got twice as much production traffic as we actually did? Or what happens if we got 10 times as much production traffic? And we can start running these experiments to really understand how our system is going to behave. And like before, it's very important to archive and preserve all of these results, and it's also important to be able to visualize them. So all of the output from Clusterman and our simulated environment goes into Jupyter and it goes into Docker. I'll show you a few examples of what this looks like. This is just a graph that we generated showing the usage for one of our clusters. This is for February 2018. And this is just a heat map showing what the capacity of the cluster looks like. And you can get this from anywhere. You don't have to use Clusterman to get this. There's lots of tools that allow you this same sort of thing. But the nice thing about Clusterman is that it gives you all the underlying data, and you can mess around with it in Jupyter. And you can see some really nice things. So for example, on the 22nd, you can see several blips where it looks like we suffered an outage. Earlier in the month, it looks like we scaled our cluster up late at night for some reason. And so looking at these things, we can start to investigate what happened in the past. And unfortunately, I don't think I can really do this justice. I'm going to skip this slide. I don't think I can do this justice just in a presentation, but as I was alluding to, Clusterman gives us the ability to ask not just what happened, but what will happen. And so this graph is the result of a simulation that I generated where we took production traffic, we made some changes to our signals, and we asked the question, if we started auto-scaling in this way, how much oversubscribed capacity would we have? Or another way of asking that question is, how many frameworks would we have that couldn't get resources? And so we were able to generate this graph, and we could say that, between 9 o'clock and 12 o'clock, it looks like we're going to have a lot of things that are competing for resources, and this is probably going to cause slowdowns in our system. And then we were able to take the results from that simulation and tweak our parameters a little bit, make some changes, and produce this graph, which is asking the exact same question, but we don't have any resource competition anymore. And so this allows us to, again, predict what's going to happen before just twiddling with parameters on your production cluster. And this, I think, is a really, really important tool for anybody who's running large-scale systems like this. So you might ask the question, well, what comes next? What comes after predictability? And since I'm on the theme of inventing buzzwords, I've invented another one, which I call feedbackability. I'm just going to walk you through, this is sort of my dream. This is my wish list. You start with your cluster. It's Mesos, it's Kubernetes, it's whatever the new hotness is. You collect data about it. This is observability. The data then goes to the users, and this is predictability. So the users are able to take that data, run simulations, do whatever they need to do with the data, and make some changes to the cluster. Feedbackability adds a machine into the loop. So what I want to get to the point where I can do is not have to have the human there analyzing the data. The machine should be able to look at the data and figure out how to tweak the parameters for my cluster in whatever ways to accomplish whatever goals I want. And of course, you still need a human there because you want to understand if this thing goes wrong, how do I fix it? Or maybe business parameters change and you need to communicate that to your machine or something like that. But really, my goal is let's automate all the things. So I talked a lot about Mesos. I talked a lot about how we use that at Yelp. But really, the core message of my talk, I think, is we should be using, as SREs, as DevOps folks, we collect a lot of data. And we should be using that data in intelligent and automatic ways to make better decisions about our infrastructure. We are hiring, so if any of the things that I talked about sounds interesting to you, please come up to me and ask me more. You can also find us on social media and on GitHub. And with that, I think I will stop. So thank you very much.
I saw that you had like GCE as well as like Azure up there, but it sounded as though you guys were pretty much on with AWS. Have you guys started to look at Mesos on top of GCE, or is that something that with all their Kubernetes, does it feel dissonant, or will you stick with your management scheduler that you use?
We have not really started looking into things besides AWS right now. The reason those were on that slide is, again, that layer of Clusterman is pluggable. So you can just write a wrapper around GCE or Azure or whatever you want, and all of the other parts of the scalar will stay the same.